You are watching the Geek Nerd podcast, and we are here to make you curious and inspire you with our deep tech talks on distributed systems, databases, stream processing, and general software engineering. Now sit back and enjoy the episode. Hey everyone, welcome to the Geek Nerd podcast. I am your host, Revolutionizing, and I'm back with another very interesting episode. Today I have Andrew Lamb with me from InfluxDB. And we are going to talk about DataFusion, the future of database system design using the FDAP stack. And we'll go deeper into each of those, what it means and why does it make sense. So welcome, Andrew. How's it going?
Thank you. No, it's going great. It's going great. I'm looking forward to this.
Awesome. So let's start with a brief introduction about your background, what you do, and what are you up to at InfluxDB?
Yeah, so I'm currently a staff software engineer at Influx Data, and I also am the chair of the newly founded Apache DataFusion project. Previously, that was a part of the Apache Arrow project, and I'm also on the PMC, which is the governance sort of body of that project. And I've been working for the last 4 years on the various technologies of the FDAP stack, which we'll talk about, both to apply them to the new version of InfluxDB, which is InfluxDB 3.0, and as well to help the underlying technologies progress, right? It would be interesting I'm looking forward to explaining how we got there from Influx and those technologies, and then there's a whole bunch of stuff about the specific technologies too, but there's also a nice broad story as well.
Yeah, so sounds good. I was reading a bit about FDAP stack, and I've also done some episodes related to analytics databases and how they work internally. But what I've found is analytics is a very overloaded term. And so let's define, when we talk about specifically DataFusion and the FDAP stack, what do we exactly mean by analytics?
Yeah, so I also come from like the database background, right? So I'm going to use a lot of database terms maybe. So let me know if there's too much jargon, but I worked for a company called Vertica for 6 years, which was a big distributed database. And I worked for Oracle earlier in my career too. At a high level, like the database people like to divide databases into two broad categories, at least I like to. One's transaction processing and one's analytic processing. So that's OLTP, if you hear people talk about that, versus OLAP, which stands for online analytic processing. I'm not sure those are necessarily the best words, but that's what gets used in the database sort of literature and terms. And the major distinction is for analytic systems, or for transaction systems, let's start with there, you do a lot of individual changes, right? They're basically designed for a high volume of transactions in this case, but that typically means like you're updating a single record. So that's the kind of database or technology that underlies a website or your bank account or whatever. And the workload is really about how many of those transactions you get through per second. Analytics is a little different, even though you often use the same language like SQL. The real focus there is not each individual transaction, read, analytic, query, whatever, touches tends to be able to touch on many more records, right? So rather than each query touching a single record, it's touching thousands, millions, billions, whatever. And so the focus of the analytic systems is often on throughput, like rows per second or whatever, rather than transactions per second. So I think that's the fundamental difference. So when we're talking about analytics, it's basically taking a large data volume and computing aggregates or statistics and finding the exact parts and slicing and dicing it for various downstream consumers, either other systems or machine learning pipelines or people or whatever.
Yeah, that makes sense. And that mental model has also helped me understand at a broad level what do we mean by transactional and analytical databases. And I also find that this line is becoming more and more blurry because the transactional systems also have some analytics features. But let's focus on the analytics part where like really large amounts of data and data is coming in at a very high velocity and all of that. Talking about the traditional way of designing analytical databases, there are like always discussions about columnar format and this compression algorithms and a little bit like optimizations at each layer, like starting from API to the storage formats. So, but what are the like general bottlenecks or the limitations when we talk about the traditional analytical system? And with this, I also want to ask, what was the reason FDAP was created?
Sure. Yes, I don't view FDAP as like a fundamental change in like the traditional analytics system, and I'll explain that in just a moment. Maybe we should talk start talking from my perspective what like this traditional analytic system is, because those workloads are very different, right? The transaction processing and analytic processing, I think there was recognition maybe 30 years ago in the database research community. Hey, if we focused on systems that were designed for the analytic workload rather than transaction workload, we can get like a 10x better performance, right? You need an order of magnitude performance improvement to justify new systems. And I think the reason transaction processing systems came first is because you need them to get the data in the first place, right? And then you had them, people started doing analytics on it, be like, oh, this is actually pretty slow. And it's not because there's anything fundamentally wrong with them. It's just the workload is very different. So there's a bunch of research that happened 30-ish or so years ago in the research community, which is like column stores, vectorized expression evaluation, encoding, and there were early versions of it, and then they subsequently were refined at various research systems. And then maybe 10 years ago, you saw the first wave of commercial systems that started taking those ideas. Right. So I worked for a company called Vertica, which was one of the companies at that time. There were other ones there's another one called Parquet, which actually is what Amazon bought that, and that's what now underlies Redshift. There's another one whose name's escaping me, but there were a couple of them in that field, but they basically were commercializing this idea of if you applied column store, encoding, some other interesting database research techniques, you could get a commercial system that goes 10x faster. And I think those companies were commercially successful to varying degrees. But then what subsequently happened is the data volume that people were dealing with has exploded, right? And the need for systems that crunch data in various other ways hasn't decreased, it's only increased. And so what you saw over the subsequent 10 years is people effectively re-implemented variations of the same technology over and over again, right? So you saw columnar file formats, right? We had one of those at Vertica, it's great, but it doesn't look that different, frankly, to something like Parquet, right? Or all the other columnar file formats. And vectorized execution, likewise, got re-implemented over and over again. I can give good examples. And you got to send the stuff over the network. So you implement like more and more examples. You do that a couple of times. And so I think by the time Paul Dix was casting around 4 or so years ago, like he wants to build a new version of InfluxDB and he wants to resolve some of the challenges with the original architecture, right? He basically saw, hey, I want an analytic engine, right? Which means columnar store and columnar file format and put on object store and a bunch of things. But he's also, you look at it, it's well understood how to do that, but it's a very expensive proposition to do in the sense that it's a lot of engineering effort, right? Even though now it's been done a bunch of times, if you look at the people who've done it, they've been very well resourced, typically venture-backed companies or big enterprises. And so without starting another company and raising however many hundreds of millions of dollars to do that, which by the way, there's definitely other companies that do it. Where do you find it? And so I think that's where the FDAP stack comes from, where those pieces that form that stack are the same components that you would need if you were going to go build an Olap system from scratch today. They're not the entire system, right? But they're like the core pieces that would take you a lot of time to implement, but don't really do a lot of value add to your system, right? Because they're basically going to look exactly the same across all the systems. So you can either redo it yourself, or ideally you can work together with a community to not have to do the standard piece. I think that's where I see it coming from.
Okay. Yeah, that makes sense. You mentioned that we have seen increased volumes of data and increased, let's say, expectations from the application users that they want to see, for example, more real-time analytics and all of that. And also cost comes into the picture. What kind of data size or velocity of data are we talking about here? If you could give some examples based on your experience.
I think by the time you're talking like millions of rows or hundreds of millions of rows, that's when you start needing this type of technology, I think. But I'm sure that exactly where that hits is probably different. But by the time you're doing something at that scale, doing it as a Python program, I love Python, but you're probably going to be like actively waiting noticeably to do things. And it's where this type of technology would come.
Okay, that makes sense. And we'll go deeper to understand how FDAP stack is able to handle such a load and high volumes of data. With this, let's understand FDAP stacks, right? The full form, right? The Flight, DataFusion, Arrow, and Parquet.
Yep.
What are these, and why do we need all of these?
Yeah. So like I said, these are like the building blocks you would need of a database. By the way, these are not the only possibilities. Each one of them is a category, and there's several other existing systems, which I'll talk about. But at a high level, so let's start with, we made FDAP because it sounds nice and it like pronounces reasonably, but I think it actually makes more sense to talk about Arrow and Parquet first, and then we build up. So the A stands for Arrow, Apache Arrow, which is an in-memory columnar format, really designed both to minimize interchange costs, but also to allow fast computation, which we can talk much more about. The P stands for Parquet, which is a columnar file format that I think is very widely adopted, and it's only going to get more so. That has a good combination of features and ecosystem support and good compression and good read speed. F stands for Flight, specifically Apache Arrow Flight. Arrow is like this in-memory format, but of course, many modern systems have multiple nodes and you have to send data across the network. And if you're not careful, the actual amount of time and effort you spend both in CPU and engineering time of just like converting the data from whatever format it is that you're processing in memory to something that you send over the network and then back into memory on the other end can take a significant amount of time. So Flight is a fast way of sending that data over the network in a columnar form that doesn't require a lot of CPU or additional engineering work. And then finally, the D stands for DataFusion, which is a query engine, which I mentioned maybe just even last week, finally became its own top-level Apache project, but it's been part of the Apache Arrow project for many years, I think 6 years now. And much like people would, if you were going to build a new programming language today, you probably wouldn't do it from scratch and build all the intermediate representations and the optimizer passes and the code generator and all that stuff. You'd probably build it on LLVM, right? Because then you can focus on what makes your language special and not worry about all the stuff that you need to have a good programming language, but isn't really differentiating. So in my mind, DataFusion does the same thing for query engines, right? Like if you want a system that runs SQL, that's actually a significant amount of effort to build, but chances are you have some other specific use case you have in mind, right? That you want SQL as part of it, but that's not really what's going to differentiate you. And so being able to build on top of a high quality engine like DataFusion that's designed to basically be extensible wherever you want allows you to spend your time innovating on whatever makes your product or project important rather than like low level database techniques for making fast group. I could go on indefinitely about how much cool stuff there is in there, but it just takes a lot of work. It takes a lot of time. And there are people who have the resources to build stuff like that, but there's not that many of them.
Okay. Yeah, that makes sense. As you mentioned, let's start with the bottommost layer, if I can say so. I don't know. Apache Parquet. And it's the disk-based storage format focused on columnar data. And so talking about other analytics database, columnar format is critical because typical analytical query would focus on a few columns and not the entire row. But what is different in Apache Parquet as compared to other columnar formats?
In my mind, Apache Parquet, the major benefit in my mind is it basically has the high level features you need out of a columnar format, which I'll enumerate in a second. And then it's got a huge ecosystem. I think, frankly, it's much better of a format than people fully appreciate. I think the format itself is very good. I think the ecosystem fragmentation around the readers and writers is not good. I have personal plans to try to help make that better, but that's probably not the content of this talk. What are the features you want out of a columnar file format? Like, why do you put it in columnar file? Typically, it gets good. It's for compression and it's for read speed. Right? So so the way you get good compression in these columnar file formats is, it sounds stupid, right? Oh, instead of putting it row by row, you put it column by column, right? But what that allows basically is, if you think about it, if you've got your data that's like a string and then a float and then an integer and then a blah, 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 and you put that all in line versus you have an integer and an integer like right next to each other, you can imagine that integer column of all the same data types that's homogeneous is going to compress a lot better. And so that's one of the mechanisms by which columnar file formats get such good compression. And plus, when you have the same data and code it, you can apply sort of specialized encodings that do even better if you know something about the files, like run length encoding or whatnot. And then when you go to read, so that's the compression side. And when you go to read the file format, you need to be fast. One of the things you just mentioned, which is projection push down, right? Which basically means if you have 100 columns in your file and you only need 4 of them, you really don't want to have to spend any time looking at the 96 that you aren't looking at, right? Like you just want to spend the time reading the 4. So Parquet lets you do that. There's also a variety of other push downs that you want to be able to do in these file formats. In particular, you want to be able to push down predicates if you can. So not just skip the columns that you're not going to read, but you also, basically the name of the game of these analytic systems is don't do as much work. Figure out how to avoid doing as much work as possible. And so one of the techniques of doing that is to basically use metadata about the information that's in the file to figure out as you have to look at every row. And so Parquet has a feature called row groups, which again is not unique to Parquet. This actually, if you're into database research geekery, it's a concept called packs, which was, I don't know, a paper from 20 years ago, but it basically divides the file into horizontal strips. Orc has the same thing. I can't remember what they call them, but they're basically these like chunks of the rows, right? So you divide, if you have 1,000,000 rows in your file, maybe you divide it into 10 groups of 100,000. And then for each one of those row groups, you encode the columns separately, but you also retain information about the values in the column, typically the min value, the max value, null counts, and sometimes some other stuff. And then using that metadata, the Parquet readers can actually look at a file and you can quickly identify, hey, there's no way whatever data I'm looking for, right, that's in this US state of Massachusetts or something, right? Like it doesn't even show up in these 100,000 rows, so I'm not even going to do anything with them. So the Parquet file format has enough of that information to be able to support the row level pushdown as well. Okay. Not just at the row group level, there's like lower level stuff too. But so it has all the major features.
So at a broad level, I see two things. Like one is definitely you get better compression because you're storing the same data type data and they get better compression. And then, so you save cost in terms of the storage space. And then with the projection push down and predicate push down, you also reduce the network cost and latency because you're ultimately only sharing data between nodes that is required and not otherwise. That makes sense. And with this, so this defines why it is compressed and high performance storage layer. Let's get up to the next level, which is the in memory. So once you have the storage done, you want to store the data in memory because you want to share, you want to do some analysis and computation on top of it. Why do we need a new memory format when we have so many? And I would also love for you to talk about the other like alternatives, what we have as compared to Arrow.
Yeah, so to be honest, I don't know of anything that's like Arrow, right? What I know is that each of the individual systems, like I come from database world, right? So I know Vertica has its own in-memory format. I know DuckDB has its own in-memory format. I know Velox has its own in-memory format. And but if you look at them, they're all basically, yes, there are some differences between Arrow, but like the vast majority of it is basically the same. Or maybe they represent nulls slightly differently or something. Like it's validity mask versus a null mask or something. But the point is, it's basically the same. Like there's not that many ways to represent an array of 8-bit integers, right? There's just not. And so having a standard way of representing that and a standard type system, right? So you don't have to redefine the type system and define the mapping between each systems. I think that's a huge source of engineering time that you don't have to spend if you use something like Arrow. I think from the Python side, there was, like, for example, NumPy arrays is a plausible alternative, right? That's widely used across the Python data science ecosystem. It's got very fast computation on it, right? We were messing around with that stuff. It's written in Fortran, right? Like it goes actually pretty fast for doing large matrix manipulations. I think the challenge is it basically only is used in the Python ecosystem, right? I'm not sure it's easy to just take subsets of columns, for example, and move out. So I don't know of actually any other technology similar to Arrow in the sense of it's trying to be a standard. I know lots of implementations that look an awful lot like what Arrow does, or maybe you say Arrow looks like a lot of what basically best practice was in the industry.
Interesting. When we talk about Arrow, there's one thing that pops up is the language, being language agnostic. And how does that help reducing the cost of the transfer?
Yeah, so what Arrow is, it's just a specification that says if you want to pass an array of 64-bit integers, here's what it looks like, right? It's a line like this, and here's how you represent nulls. And it has that for like date times and structured types and floats and strings and all that sort of stuff. So that's all it is at the end of the day. Yeah. And so now the question is, when you're writing a Python program and the data came from Rust, right? How do you quickly get the data that came out of Rust into Python? And the way it works with Arrow is that or C++, right? I'm a Rust guy, but like C++ generates data in memory in the Arrow format, and then it sends a small amount of information along with the pointer to the underlying buffer to the Python library. And the Python library then just basically uses the data as is, doesn't have to modify the data, and it has the native Python bindings. Python's actually binding on top of the C++ implementation, but it has the bindings there. There's no translation that's required, and it just goes off and does whatever is appropriate for that implementation. So I think there's 7 native implementations of Rust, of Arrow, they're governed as part of the Apache Arrow project. There's at least 2 of them that I know that are not. I'm sure there's more, but there's at least 2 implementations that aren't actually even part of Apache, right? Like it's a standard. People can implement it however they want. And then there's another 4 or 5 implementations that are basically bindings on top of the C++ implementation. So like the Python and Ruby and C is actually a binding on top of but like the Rust implementation of Arrow, for example, is entirely native Rust, right? It doesn't bind. It's not like a binding on top of the C++ or anything. And so that means it behaves like you'd expect a Rust library to behave. And likewise, the C#
Okay.
one behaves like you expect a C# library to behave, not something that got shoehorned into a C++ API.
Interesting. So it makes sense because it removes the cost of translation between different formats because it's just one standard format. And since you have, let's say, clients in different languages, it makes it easier and removes this translation cost. I'm wondering if we talk about analytics use case, talking about the disk storage, probably it makes sense, at least in my mind, to have it in a columnar format and so that you avoid the IO and make it faster. Why do we need columnar format in memory?
Yeah, excellent question. So in addition to just the interoperability, avoiding translation costs that you just highlighted, the other thing that columnar formats in general, and I'll talk about Arrow specifically in a second, allow you to do is the way modern CPUs work typically is that they don't just do they don't just operate on one little piece of data at a time. They typically have specialized instructions that operate on multiple ones, right? So there's SIMD instructions at a high level, and you call them a lot of different things, but basically like the AVX instructions in Intel, and I'm sure there's other ones that I don't even know. But so hardware is specialized for doing the same thing on a bunch of data over and over again, right? And so columnar file formats let you do that, right? They're basically just big contiguous swaths of array numbers or whatever that you want to do something, you just do it on 1,000,000 of those things in a tight loop, and the hardware can really you can take full advantage of your hardware. Versus in a row format, you got to look where you got to go, figure out where it is in memory, run the operation, find the next row, figure out where the relevant value is, go do the operation. So there's a bunch of overhead per row that you skip with a columnar format. And that general idea of not having row level overhead, like that's, I think, often what people mean when they talk about vectorized processing. So rather than sitting in a loop like for each row, do this, it ends up being like for each column, go do some operation. And I think that's
That
one of the areas where Arrow really helps.
yeah.
Like the other thing about Arrow that's not really part of the standard, but is part of a lot of the implementations is these low-level computation kernels, which sounds like it's like low-level geekery. It's like I got 2 of these and I want to find the places where one array is less than the other or whatever. But there's, I think, 60 of those types of operations in the Arrow Rust implementation, for example. And they each one just like someone obsessed about making it fast. And so now when you want to go do comparison against these things, you just call these functions, they do the thing. You don't have to worry that someone dealt with if there's nulls, there's a special case. And if there's not nulls, or if there's a bunch of stuff like trickery that you can do to make them fast. But having a standard right now, you don't have to go re-implement all that stuff.
Interesting. What if I have to do the communication between, let's say, two platforms that do
Yes.
not support Apache Arrow? One of them supports Apache Arrow, but not the other one.
Yeah. In that case, the one that doesn't support it, you have to write a program to do it. It's in some ways, it's like if you start with the question of like they talk different data formats, like what do? You have to write the translation layer, right? That's what you have to do. And I think you can draw the picture like before Arrow or before something like what do? You basically have a huge plugin ecosystem for something, right? And it just knows how to talk to all the other different systems. But the problem is then if you want to have an ecosystem of those tools, each one, it's like an n squared problem, right? Like each one has to have the translation to each of the other ones somehow.
Yeah.
And so practically speaking, that means you only have a translation to a few other ones. And so people's data gets kind of like stuck in some part of that ecosystem. Whereas you got something like Arrow, and I think now it's gained enough traction. It's basically any Python program you care about can generate data as Arrow, right? And now you can put it in, You can send it to DataFusion, or you send it to Polars, or you send it to DuckDB, or you send it to Pandas, or a million other tools I've never heard of, probably, or your machine learning pipelines, right? Just all, and you just don't have to think about it. They all just deal with Arrow. Polars doesn't have to know anything about whatever you're doing with the data downstream.
Interesting. I guess what I wanted to ask is in more of a migration scenario where I already have a system and now I want to use Apache Arrow, but parts of the system I cannot really directly re-implement, for example.
Yeah.
So in that case, do we have already support for translation between Apache Arrow and some other formats?
I think so. People have implemented stuff like translation of for example, the Postgres wire protocol into Arrow. That's not a particularly fast operation to do, but you can do it. And then you can imagine now you can have systems that talk Arrow, talk directly to things that know how to talk to a Postgres wire protocol. I think the problem you're describing, though, like I already have a system that talks one thing and I don't want to have to re-implement it. I actually think that's more of a problem for systems that store the data. Right? So for Arrow, the data is like flowing through the systems anyway. And in some, you can persist Arrow, but realistically, most people, it's like some ephemeral thing while you're doing processing. The real challenge is you've got a pile of data somewhere and it's in some proprietary format or some custom format. What do you do with that? So I think that's actually the place that Parquet, I think, really shines. Like we're already seeing it in my mind, and I think we're only going to see it over the next 4 or 5 years, is the way people are going to store data is not in individual databases anymore. They're going to store it in Parquet files on object store like S3 or GCP Cloud, whatever it's called, because the economics of it are super. You basically can't beat the economics of it in terms of the storage cost. And you're going to have all these tools that know how to read Parquet and they know how to talk to object store. And so consequently, that will become the equivalent of Arrow during processing, transferring data back and forth. This will be like you just point your tool at whatever pile of files you have on S3, probably using like a table format like Apache Iceberg or something. And then that tool is going to go do whatever it does using the data in that format.
Interesting. You mentioned an interesting point that you could also persist Apache Arrow. And then that brought me to a question, which is probably a naive question, but I'll still ask you. How does Apache Parquet compare with Apache Arrow? If I like both are columnar,
Mm-hmm.
and I believe Arrow can also be persisted to disk. So why do we need both? What is the
Yes,
difference?
excellent question. The short answer is because Arrow is designed for in-memory processing, so it's actually doing operations on it. For example, picking some an arbitrary row in a big Arrow array is like an order one operation because they're basically all fixed size, so you just immediately go to it. Apache Parquet, because it's got such highly effective coding and compression, to get a value out, you typically got to do a whole lot of work. And so that's great. So that's how it gets such good compression. But consequently, it means if you want to operate on it, you need to do a bunch more work. And so I think that's the typical trade-off. So we've invested a lot of time at contributing upstream at Influx, and other people have too, of how do you quickly get data that's encoded into Arrow, because then you're going to go to operate on the Arrow. But it's really important to be able to translate from one to the other quickly. But then it's actually beautiful, right? Because now you got your data in Arrow, you do whatever you want, and now you send it back to Parquet, and so that becomes you've got your storage format, you've got your in-memory format. Which, by the way, like columnar database systems have exactly the same split, right? They have an in-memory representation, they have an on-disk columnar. They're both columnar, but they have different details because they've got different designs.
Yeah, I think that makes sense. When typically talking about these analytics workload, right, majority of the data is not really like mutable. So once it is there in the system, you don't want to change the data. But I've seen use cases where mutation of data is also required. And some, there are different ways different systems do it. But I always find it interesting, like how it is done, because it's all, let's say, optimized for storage. We're compressing the data. So mutation becomes a lot more expensive. How does Arrow and Parquet deal with it?
Yep. So you're absolutely right in the sense that another technique that's used in these analytic systems, almost all of them, is that the data is immutable. So that, and the immutable meaning it doesn't mean you can never change it. What it means is that once you've written it, in order to change it, you basically have to write another copy of it and you throw the whole thing away. So once you've written a version of it, you never change it. And the reason systems do this is because the alternative is if you want to have multiple people, if you're reading it and modifying it at the same time, you have to add a bunch of complexity to do concurrency control, right? And like basically prevent people from interfering with each other somehow. And that's often very expensive, or like depending on how you do it, it can be very expensive and very complicated. So a lot of the analytic systems, especially because they're not designed for lots of little tiny transactions, they're designed for small numbers of giant reads, they go with immutable storage, and that translates into memory, right? So an arrow is basically the same thing. It basically says, I don't think there's anything about the memory format itself that requires you never change it, but all the implementations basically, like you get the data and you don't modify it. And that lets you share it. Everything's great, but it does mean when you actually have to go around till the real world happens, right? That you need to update data or something, right? Like you have to that becomes much more complicated in an analytic system. So the typical way that the systems handle it is you model a delete as an insert, right? Which is weird. Instead of actually deleting something, what you do is you tend to add something that's called a tombstone, or like we call it a delete vector in Vertica, but it's all basically the same thing. You put a new marker somewhere that says, hey, this row is actually deleted. And then when you then during query processing, when you're actually reading the data, you have to have extra logic in there to while you read the data out, to check this little thing, the additional list of ones that have actually been deleted, and filter them out. So that's the high level strategy of how it tends to work. You model, by the way, updates as an insert or a delete followed by an insert, right? So all you really have to do is model. We don't have to talk about deletes. And the downside with that is actually if your goal is to, like, for example, reclaim data or conform to GDPR and actually get rid of things, right? That didn't help you because you didn't actually get rid of any data. You just added some new stuff. So the way systems will do it is they'll have some sort of garbage collector thing that runs around and compacts the files. And so what they'll do is they'll read the original copy, filter out anything that was actually deleted, and write a new file, and then delete the whole entire old one. And then new queries will refer to the new file, and eventually the old one will get cleaned up. And I think that high level pattern exists in basically every analytic system I know about. And I think depending on exactly what use case they're targeting, right, there's all sorts of variation you can imagine of maybe they're, like, for example, in a time series database, the most recent data is actually the one that's also the most likely to get updated. And so it probably makes sense perhaps to keep that in memory buffer that you can modify for a while. And then after some period of time, you close it and you write it to some format that's more efficient longer term, but it's harder to update. So that's like, we do that in Influx as an example. But I also think that's another example of why it's so valuable to have these common pieces all together. For the particular time series use case, you can go focus on time series and get 10x better than a general purpose system, and that justifies time series databases. And the same, like for streaming systems, you do the same thing, or for JSON processing systems or event systems or whatever. And so I think that's one of the reasons we've seen the proliferation of these large number of databases, is because people recognize if you focus your efforts on some particular use case, you can get it to go 10x faster, which, like I said, I think is basically the bar for justifying a new system. But that also now means, like, we got 1 million databases, right? So I think that's part of also the pull towards having, if you had 1 million databases, it's fine, right? You have lots of different tools and options. If they can all read, but you don't have to, every time you want to use a new tool, move the data from one to another, right? It's all in Parquet on S3, for example. Now you have a very compelling story. You pick whatever tool you need that's best for your workload. They all read and write the data to the same place, but you care about low latency stuff. You can get one that has a fancy caching system, or you need to update a lot of stuff like this. You could imagine spending lots of time with specialized systems that were optimized for those workloads.
Yeah, that is definitely interesting. And I've seen, like, the approaches that you mentioned, I've seen in different systems as well. And I think understanding the workloads that you're dealing with is more important. And at least in my experience, majority of them were fine with not being able to mutate data. There was one use case where it was really required. It was also delete heavy and update heavy scenario. But still, if I compare with read queries, that was way higher. Cool. Let's move on a bit on the upper layer. So I have the memory format, I have the storage layer. Both are awesome because there is, like, very specifically designed for analytical use cases. They provide better compression and better random access and vectorized computation and all of that. Now so once I have the data in storage, I want it in memory. And once I have it in memory, I want to give it a user interface so people can query it, or rather even move across the networks. So there comes DataFusion and Flight.
Yep.
So let's talk about that. I'm not sure which one is on top. Probably.
I think they're both. Could talk at either one next. I don't know if there's a clear order.
Okay. Okay.
How about we talk about flight first as a high level thing, and then we spend a bunch of time with DataFusion. So flight, there's a couple of things about flight I'd like to talk about. The first is just it's simple. Like you want to send this data that you have as arrow arrays, like because you read it into pandas or whatever, and you want to send it to some system to process it or insert it to the data or something database. It's pretty sweet to just literally take the same memory bytes that you're going to stuff those on the wire. Don't have to marshal them or unmarshal them or anything. Just send them over and the receiving end does the same thing, right? Just gets information in, make sure it's valid arrow, and then you can just go and process it. That's like the high level overview of what flight is. Now, like what benefits do people get? The very first thing is if you're like, I don't know, a database, for example, and you want to let people insert large volumes of data as arrow arrays, you implement your side. But now you also immediately get access to the 15 client languages that have flight clients, right? And so now someone wants to write a Ruby program that sends data to your database. You don't have to go re-implement, find someone in Ruby who knows what they're doing, have them re-implement whatever protocol you just invented, right? No, there's already one that does flight and you just send it over the network. So that to me is the major benefit to the implementers, right? Yes, it's fast, but frankly, if you sat down, you could implement another protocol that's just as fast, probably better. People have to play with stuff. But I don't think there's anything fundamental technical about it that's earth-shattering. What's really important is that there's a huge library of existing clients and it's a standard. And so for example, in Vertica, we had a whole team that was responsible for the client library because we had some variation of the Postgres wire protocol. And I think we had one guy half time did it for Influx. Not even, because all it does is the Influx DB30 client is just a flight client with some extra APIs that let you do some that are Influx specific. But basically, all the actual data manipulation and sending is all handled by the underlying flight client. So in addition to flight's kind of like a building block. I'm not sure you'd ever say two things could interoperate with flight. It's like a thing that you'd build your protocol on top of. However, one of the things that's very important that got built on top of flight is flight SQL, which is like a layer on top of flight. And it basically it defines the format of the messages, like the metadata messages that go back and forth. But again, there the value is if you know, like before flight, right? And you had your database, what do? You make your database, everything's great. Now you have clients that you want to talk to it. You have to go basically implement clients for each one of the languages. Old school, old guys like me would talk about JDBC and ODBC and whatever, right? The maybe more modern stuff is you tend to implement a special one for pip, and there's not pip, whatever that's called, PDB, whatever there's like a Python database API that people would implement. And there's a similar one for C#, and there's a similar one for all the basic language ecosystems. And that lends you a challenge, right? As a new database vendor, you either got to invest heavily in a whole bunch of different clients for a bunch of different database languages, or you're just going to have to restrict your customers to only a certain subset of the languages. And typically you end up doing both, from my experience. And so Flight SQL is basically like there's a Flight SQL JDBC client, there's a Flight SQL ODBC client, there's a Flight SQL Python client. And so you want someone to send SQL to your database and get results back. They just use the Flight SQL client. You want Flight SQL on your side. And so that's actually what we've done in FluxDB3. And again, like we have a JDBC client without ever having to implement JDBC, which there's been various opinions on the internet but we definitely had a team that there's a company called Simba actually who specializes in helping people implement like JDBC and ODBC. So it gives you some sense that it's a non-trivial endeavor typically. And so not having to do it is great, right? Like we spend a bunch of time on doing time series stuff, not JDBC clients.
That's great. I'm particularly curious about the SQL support.
Yes.
So because that is again overloaded, and there's like a different spectrum. What kind of SQL support do we have?
Yes.
But when we say SQL support, is it like full SQL support where we also join from different data sets and all of that?
Yeah. So let's talk about the level of SQL support as part of DataFusion. Let me just finish up Flight for a second, and then we'll launch into that. Flight, when you like the way Flight SQL works is you send a SQL string, like it's like literally a string, and the other system is responsible for interpreting it. So it doesn't say anything about what parts of SQL are supported. Now, I should point out another popular trend in implementing database clients is that you again, we're not the only people, like you're implementing a database and you recognize you don't want to go implement your own clients again. A very common thing that people have done recently, especially with the rise of Postgres and its permissive license, is they'll say, hey, you know what, Postgres has a great client ecosystem. All the licensing is fine. It's well understood. The ecosystem support is great. What I'll do is on our database, right, we'll implement the Postgres wire protocol, which is the network protocol that the Postgres client and server used to talk to each other, often called the front end. I believe it's officially called the front end back end protocol, or Phoebe, for your party trivia if you care. But anyway, so people will do that, and actually the protocol is pretty simple. It's easy to implement. But what they'll find is the first time they connect the Postgres client to their server, they get a whole bunch of weird SQL that talks about PG underscore blah, blah, blah tables. And what it is the client sitting there trying to get information about metadata, because part of the JDBC and AD metadata, like what types are supported, how big can you make strings, like all that stuff, which is part of the client driver needs to know that. The way the Postgres clients are implemented is they go talk to the Postgres metadata tables, which are absolutely not standard, right? There's some Postgres specific thing. And so people get lost. So you can get a demoware working very easily, right? You get it working enough, but as soon as people try to use it against real programs, it gets like you end up having to implement a huge amount of the Postgres metadata API, aka their special virtual table things that in order to actually get your client to work right. It's not so that's actually the main piece of what's in Flight SQL is the standardization of that metadata, like what types are supported, can you make prepared statements, and all that kind of stuff. All right, and then we talk about SQL compatibility, right? I'll switch now. We talk about DataFusion. All right. So, as you were hinting at, probably if any system ever claimed to fully support SQL, they should never do that. Is my conclusion. And the reason they should never do that is because SQL, yes, there's a standard. I know of no implementation, regardless of whatever vendors claim, that actually implements the full specification. Now, to be honest, I'm not sure I could really prove that, because if you ever tried to read the SQL specification, it's written in some crazy Byzantine legalese thing. Like I don't, it's not easy to read for that and a bunch of other reasons. As you point out, there's SQL, and then there's basically all the SQL dialects, right? So there's a subset of SQL that most people support, but then there's a huge variation and tail of both features, but also like the semantics of individual functions are vary widely from dialect to dialect. But yeah, so I'm not sure DataFusion solves that particular problem. I can talk about that. Let's start with, first of all, like what DataFusion is, and then we can talk about some of the nuances of exactly how much SQL it supports. Spoiler, it does do joins, it does all the basic stuff. So when you want to write a database engine, right, let's take a step back. If you want to write SQL and you want to have something that actually applies, figures out what that SQL means based off whatever data you have, and actually then will calculate whatever the SQL query wants, I would call that a database engine, right? Because like that's the database query engine in particular. There's actually, it's an important piece of databases, but it's not the only piece, right? It's like other major pieces that exist in database systems are like typically like storage managers, right? Like the thing that actually creates the data and manages it and does whatever this background compacting stuff we talked about, right? Oftentimes there's like concurrency control where you have to manage people modifying stuff at the same time. There's probably a memory manager hanging out somewhere. There's client libraries, right? There's a whole bunch of other stuff that if you actually want to make a database system that people could like start on their computer and do something useful with, that you would need to build. So DataFusion is not a database system. It's just the query engine part. So if you want to build a new database, you can, and there's quite a few companies that have done it now, build a system on top of DataFusion that plugs in like where the data comes from, where it's going to, how a bunch of the other pieces that aren't there. Networked potentially, right? You want to run distributed processing, DataFusion doesn't do that. But then all the low level details of like, you got to go type coercion, you got to make all the operators match, and you got to call the right arrow kernels with the right types, and blah 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 blah. Like all that stuff is, and you got to do all the standard optimizations. Like if you write a constant in the expression, you should evaluate it like once rather than on every row. Right? There's a whole raft of things that you need to actually get like a competitive query engine, and so that's what DataFusion has. So you basically give it data, you have to tell it what the tables are or whatever, tell it where the data comes from, and then you give it SQL, or you can actually use it to, you can either give it SQL and it has its own SQL planner. One of the big parts about DataFusion, however, is it's been designed to be extended basically in all, at every point. So what you can also do is if you don't want SQL, for example, you want to write I don't know, a time series specific query language like InfluxQL as an example. You can write your own thing, which takes the string that was InfluxQL and turns it into what's called a logical plan, which is all specific to whatever the semantics of InfluxQL are. But then as soon as that, like then all the basic, like we got to do constant folding, we got to do type coercion, we got to figure out how to do the joins and do fast group bys and reaggregate, use all the cores correctly. Like all that stuff is actually all shared. So DataFusion has this notion of it's got all the pieces built in, but then it's also, you can basically, as basic pieces built in for everything. And if you want to extend it in particular ways, the APIs exist to do that too. And so I think it's been a very effective thing. I feel like I rambled there a little bit. Sorry.
No, I think it makes sense because it gives you, like, it takes away a lot of, let's say, burden from you where you have to implement or support different clients, and you can plug and play depending on what you exactly want to support. And that, I think, makes a lot of sense for someone who wants to create, let's say, I don't know, solve a specific use case and create this query language, and they get a lot of these features for free. I think the FDAP architecture makes sense given for the analytics specific use cases. And but I understand about the Apache Parquet layer. But are these the other three layers or components tightly coupled with each other, or you can remove one and play with the other?
So DataFusion uses Arrow internally. So like the way you actually, it comes with a reader to read Parquet, right? Like it knows how to do all that stuff. But if you wanted to give it, like, for example, your own file format, which other people have done, the interface that you use to provide data to DataFusion is actually Arrow record batches. So in that sense, like DataFusion is very tied to Arrow. Like they would never use something different. It's not tied to Parquet, right? You don't have to use Parquet with DataFusion.
Yeah.
You can use DataFusion trying to be useful to people comes with, like, it knows how to support, it knows how to read JSON and Parquet and CSV and Avro, I think, are the major ones. But we have plenty of people who either use their own file format or have their own like indexing layer or something on top of Parquet files that they use that they don't use the Parquet readers that comes directly with DataFusion, but they use the lower level APIs themselves to implement whatever special API. So I think in terms of like DataFusion and Arrow are very, DataFusion absolutely uses Arrow. I think Parquet is not tied to Arrow. The specification necessarily has like its own type system, for example. It's different than Arrow. However, I think if you actually, like any system that stored data in Parquet, in order to do something with it, you have to read it out, turn it into some other format you can actually process on. So I think that Arrow is the obvious choice for that. And so I think a lot of the Parquet readers have a way to read and write Arrow quite easily. But I don't think there's anything that's actually required for that. But again, if you wanted to do it yourself, maybe it makes sense, but you're going to spend a lot of time doing some tight integration with the low-level Parquet reader. And then Flight is the same thing. It's definitely tied to Arrow, right? Because you have to pass data over Arrow, but it's only really necessary if you're going to be sending data over the network. Maybe your application needs that, maybe it doesn't. And I think you could certainly come up with other formats to send over the network if you didn't want to use Arrow or Flight. But like you would imagine that there has to be some compelling reason to go re-implement it yourself. Yeah, we just actually wrote a paper that got accepted to Sigma, which is one of the big database conferences, which I'm very excited about. But it basically makes the case that one of the reasons you might say, hey, doing something like DataFusion is not a good idea is because if you built a really specialized system, you could basically by having it all extendable and using all these open standards, you're leaving a lot of performance on the table. Right? That would be a natural. I've definitely heard that from various people in the database community. And I think we did experiments to show this, that in theory, that's true for sure. But the practical reality is the thing that is limiting the performance of most database systems is not the raw under level. It's like the actual amount of engineering effort they're able to put into implementing the pieces, right? So we show we're basically the equivalent performance as DuckDB when we're reading Parquet files. And sometimes they're faster, sometimes DataFusion is faster, but it's basically the same is the conclusion of the paper. And I think that's a interesting data point to show that you can use these open standards. And yes, maybe if you had some super specialized thing, you could, in theory, do much better. But the practical reality is there's very few people who have the engineering resources to be able to to really realize some major benefit over, I don't know, there's 500 people that have contributed to DataFusion over the course of time. It depends on how you count, but there's a lot of people, right? We've put a lot of effort in there. And so, yes, there are companies that plausibly could invest more, but there's not that many of them, right? It's measured in like hundreds of millions of dollars kind of investment.
Interesting. Do you know of any use case apart from analytics that is using FDAP?
I know there's a bunch of companies that have been using the DataFusion engine for streaming, which I'm not like streaming engines. So I'm not in particular things that look similar to Apache Flink. So I'm not sure if that qualifies as streaming in your mind, but that's or analytics, but that's definitely a use case that's come up a bunch, and that I know people are actively working on. There's people that are working on vector databases, but I think that perhaps falls under the analytics category. I vaguely know of some companies that are trying to do what would be called, I think they call it HTAP or something. I can't remember what the database name is, but basically there's also like at a high level, right? If you have an analytics system and a transaction system, you can understand the reason for two different systems because there's such different workloads. But the operation that now you got to have two databases. Now you have two databases, right? You got to get data back and forth between them, and so ideally, right, you'd want a single database that does everything. That's the ideal. Given the fact that we don't have a single database that does everything, suggests maybe that's not that easy. But there are systems that try, and I think they tend to be called HTAP. So like SAP has a giant thing called HANA, which is like underlies all its business applications, but it has some version of that where it's got both transaction processing ability and Olap type features. I think HANA is so big, I struggle to concisely summarize everything it has. But I think there's other people who are trying to build something similar like that on top of DataFusion, as I understand. But a lot of those are not open, so I don't really know.
Okay, that makes sense. What's in the future? Because there's definitely a lot of development going on at each layer. So what can we expect in the future?
I think I already said one of the major things I think is going to happen is that the way data is stored, especially in data lakes, right? Probably not operational storage, but the way people are going to do analytics is they're going to do it from Parquet files and object store. And I think that is going to be like, it's entirely driven by cost, right? Like it's just compared to the amount of money you have to spend to put all your data in Snowflake versus how much it costs to put on S3 and Parquet files. It's just like stupidly cheap to put on S3. Like you probably don't even like you regularly forget about terabytes of data in there because it's so cheap, right? So I think that's happening, and the economics are going to drive it. I think the other thing that's going to happen is that as DataFusion and other similar technologies, like there's a project called Velox from Facebook that has a similar piece, and there's something called Calcite, which has another version of it. So there's other pieces that are similar. As those become more and more widely available and used, I think we'll see a proliferation of new tools in the analytics space. Much like the last 5 or 10 years, I think we've seen like a renaissance in new programming languages, right? Like basically there were no new programming languages for a while. Then all of a sudden there's Rust and Zig and Julia and like all sorts of cool stuff. What's underneath all of them is LLVM. And I think the reason you can see the proliferation of programming languages is because now people can actually invest their time innovating in things that are interesting rather than implement the same low-level technology. I personally hope and believe that's what's going to happen in databases as well. It's already happening, but DataFusion is not just, it's cheaper than building it yourself, which is definitely true, but I think it's also because then it lowers the bar. Many more projects will become possible that can get access to this basically cutting edge analytic technology that you never would have been able to build before because you just couldn't have afforded to build the engine, right? So I would expect to see major innovation in like query languages. People love to reinvent SQL over and over again. I think we can talk about the philosophy, whether that's a good thing or not. Part of why a lot of those systems fail is because they have to not just invent the query language, then you got to also go re-implement all the actual analytic execution stuff under the covers, right? So you, like the performance of whatever new language you come up with is tightly bound to whatever implementation you're able to pull off, which it's just tough. So now, if you're freed from having to do all the low-level stuff and just focus on the experience, I think it'll be great. And so that's what I hope is coming. Realistically, if you look at some of the big projects that are making major changes recently, I would actually say they're not quite the same, but they're similar ideas. So I like to think about Polars and DuckDB. Polars uses Arrow, right? So that's an example of they didn't have to reinvent their own memory format, but they basically have the equivalent of Olap engine inside, and they built it themselves. It would have been great if they used DataFusion. I think for a variety of reasons, DataFusion wasn't quite ready when Richie was hacking on that thing. And similarly, like DuckDB is another example where it's basically a tightly integrated system that has one of these high hardcore Olap engines in it, but it's just expensive to build, right? You look at like from them, there's not that many people who are like come out of the CWI, which is one of the premier database research institutions in the world, and have access to a bunch of grad students in the top database CS class. The point is like having someone else build something like DuckDB it would be very challenging, I think. More super kudos to those guys to build it, but what that takes is it's very rare to have that level of technology available. I hope there'll be similar things, right, that get built on top of DataFusion that are, you can imagine all sorts of crazy uses, right? Because it's in Rust, you can embed it basically anywhere, very low resource. So you could maybe you could put on web workers all over the world, or you can, I've been toying with a buddy of mine to put it in, you can imagine an S3 proxy, right? The proxies to S3 locally, right? That maybe caches the files or whatever to save you some network costs. But if you've got that now, why not put an embedded DataFusion in there and implement like S3 select locally? And now all of a sudden it's starting to sound like, and that's 3 lines of config, 3 lines of configurable integration rather than have to go build some query engine thing. I think that we're just going to see more and more of these types of applications get built.
Yeah, very interesting. And I like the analogy you gave with programming languages, because I totally agree with that. Andrew, it's been a pleasure to talk to you and learn more about FDAP stack. And I'm really looking forward to the new features that are coming up, and also new, let's say, systems that are built on top of FDAP and using this architecture. And it really looks very promising. So thanks for joining me today. And for our viewers, if you want to check more or learn more about DataFusion and FDAP, there's definitely a lot of blogs and documentation on InfluxDB website. So do check them out, and probably also reach out to Andrew if there are questions. And yeah, thanks a lot.
Thank you for having me. I had a great time.